Hello, my name is Eneko Sedano, and the article that my team and I were working on is called Use of a GIS-based solution for the design of preventive conservation plans in heritage constructions. Here we present a brief index with the different points that are going to be treated during the presentation, beginning with the motivation and the objectives we were looking for dealing with this field of heritage conservation, until the elaboration of a preventive conservation plan through the development of an automatic workflow for the evaluation of risks damages. The main motivation for this scientific work is based on the current situation which nowadays confronts the heritage conservation. This state is defined by a huge imbalance between funds dedicated to preserve our heritage and the funds that would be truly necessary to conserve it. In addition to the recent sanitary crisis, it has been motivated a search of new methods using multidisciplinary approaches through the employment of TICs. Here is where preventive conservation appears as periodic inspections and a regular maintenance on the heritage buildings, saving between 40 to 70% of the total maintenance costs of a major intervention. To reach this aim, geographical information system approaches are going to be used to manage the evaluation of risk detected over the case study. And as a result, it is going to be elaborated a preventive conservation plan. To put in practice these steps, it has been necessary to choose a heritage building which has been previously inspected and which requires from maintenance tasks. For this reason, it has been selected the Church of San Pedro, a medieval church located on the village of Becerril del Carpio in the north of Spain. This Romanesque Gothic building was recognized as part of the cultural heritage of the country, and it suffered from several damages on its roof as well as from a settlement on its northern facade, due to structural movements and a modification in the properties of the soil on which it stands. Because of the cracks and deformations shown as consequences, all the complex had to be reinforced in 2011. It has been required the combination of two geographical approaches for obtaining the necessary sources of information. The first one, a 3D point cloud and its orthophotos obtained by structure from motion. And the second one, with the application of geographic information systems through the use of the open source QGIS platform to process and manage the required multi-source data to elaborate the risk evaluation. To proceed with the compilation of damages information, a classification of data into different save files is required and is established as follows: the planimetry, the detected damages by inspected element, building inspected field, and the assets inspection field. To reach this purpose, it has been essential the use of an QGIS application complement known as QField. This multifunctional tool allowed us to improve fieldwork by not only collecting and mapping online and offline data, but also to directly take images from the damages detected. Once the inspection has been done and the information is transferred into the computer program QGIS, the workflow for the risk evaluation can be established in a next step. All this data is collected and classified on several field attributes on each shapefile, defining the necessary data to elaborate the risk evaluation through the QGIS graphical modeler named Model Builder. This Python language complement provides an interactive interface on which is possible to load, connect, and run different algorithms as it is shown on the screen. The workflow implemented for the risk analysis starts with the introduction of the required input parameters as vector layers. These layers are the shapefiles established as inputs: building inspection field, assets inspection field, and detected damages by inspected element. Then, the algorithm update field is used in different phases of the workflow, applying the corresponding formula to determine the degree of condition of each damage, make the sum of all the degrees for each element, determine the respective state situation of each field, also determine the risk, and round off the final results. Finally, the results of the risk are shown in a visual and intuitive way through the algorithm established style for vector layer, substituting the colors of the initial cartography. Once the risk analysis operations have been developed and computed, the design of the preventive conservation plan of the charge is finally performed, having the following structure. In a first step, a brief description and a summary of the situation and documentation of the case study is created. Then, a compilation of 4 risk evaluation files. As it is shown on the screen, the risk results carried out showed that the roof covering, the rainwater system, the building envelope, and the indoor climate present a high risk, so their intervention must be immediate. A set of 37 damages files contain in detail the kind of damages detected during the on-site inspection, its location, the risk evaluation for each damage, the final state condition, and a series of possible consequences if the intervention is not realized, as well as several maintenance tips with some on-site images from the detected damage. Among the previous risk results and the damages files obtained, it is observed that the critical situations are caused by losses of material due to humidity and filtrations, damages which can be originate biological colonizations, like the ones which appeared in the sacristy walls, with the growth of algae. To solve it, it's recommended a diary or weekly ventilation and control, realized by the charge owner. Another relevant damages are the cracks and fractures caused by the settlement of the charge structure. So, as a solution, it's recommended to install tilt sensors to control the deformation of the structure, trying to avoid an awful collapse. Other elements classified with a high risk are caused by detachments or spellings, so it's recommended a regular revision of those elements or a replacement of the most damaged ones. As a summary file, it is designed a maintenance calendar classifying the different tasks and recommendations depending on its frequency. Moreover, a Gantt diagram is elaborated as a visual programmation with the principal tasks to realize over the year. Finally, this article has allowed us to discover, on a first step, the efficient combination of two technological information approaches for the design of a preventive conservation plan for San Pedro Church, using QGIS and Python language. This strategy combined with additional workflows and apps to standardize and improve the interoperability of the data as well as the data capturing in field. The present work proposes the use of standardized damages documents and files by using in-house programming scripts through the QGIS Modeler Builder. And eventually, as a result of the risks evaluation, it could be possible to prove the efficiency of the visualization of risks damages, combining visual geomapping with geographical information systems, allowing us to design the preventive conservation plan, not only prioritizing the most urgent conservation activities, but also designing easy reading report for the owner of the case study. Thank you for your attention. We, the authors, would like to thank the Santa Maria la Real Foundation for providing us part of the necessary data for this research study. We would also like to thank the ELISA project, or European Engineering, Learning, Innovation and Science Alliance. More specifically, this activity was enclosed within the framework of the ELISA Sustainable BCC community. If there is any question, do not hesitate to contact us through our emails. Thank you.